Welcome. In this video I'm going to talk a little bit about Cramer's fee for a goodness of fit test, so not for a test of independence, which is an effect size used for analyzing a nominal variable, or could be used as one. In this video I will only quickly go over the basics of this, how to actually determine it using different software packages. I have separate videos for those. Now, in previous videos, I've been working with an example about marital status, and these were the results from a survey. We also visualized those in a nice bar chart and also performed the Pearson chi-square test of goodness of fit. And that one was to be significant. It was below 0.001, which indicated that they're not equally distributed. How to perform that test? There's a separate video on that as well. In this video, we're going to have a look at, okay, so there are differences, but how big can these differences be classified as? And that is to some extent what effect sizes do. So there are actually three that I've come across that could be used as an effect size. The Cramer's fee, the one that we're using in this video. Cohen's W, which is an alternative one. The advantage there is that it doesn't depend on the number of categories. And Johnson, Berry, Mielke, E, which is not so common, but it has as a huge advantage that it will always be between 0 and 1, and that's a quality for effect sizes many people actually like. But the focus for this video will be on Cramer's fee. So Cramer's fee is named after Harold Cramér, who was Swedish, lived from 1893 to 1985. And of special interest is his article from 1946, where on page 282 he actually defines his fee. But however, this was for a contingency table, so for a chi-square test of independent, not for goodness of fit. However, some will claim, for example, Mangiafico, I hope I pronounced that correct, he actually mentions that it can be modified to also use for a goodness of fit test. It needs to be then slightly differently calculated. Here's the formula for it. It takes a chi-square value that was already calculated with the chi-square test of goodness of fit. It requires the sample size n and then multiplied with the number of categories k minus 1. So this formula looks perhaps a little bit daunting, but it's actually not that complicated. Of course, for the calculations, you can use different software packages. On my website, peterstatistics.com, just as one go without the space and then .com. If you go for one variable and then select a nominal variable, you get a nice menu on the left hand side here, and one of those is options is their effect size, and there I explain the effect size for the analysis of a single nominal variable. In there you will find somewhere saying click here to see how it can be done, and then there are a few different software packages, and if you click on any of them it will show a video on how you can actually obtain Cramer's fee. With SPSS, it's a little bit tricky because it doesn't calculate it in one go for the goodness of fit. So as you can see, eventually you will need a little bit of Excel, but the end result will then simply be a number. You can use then some of the output that is in SPSS. If you use R, you can have different packages or calculate it almost step by step. But as you can see, all of those have the same result. So here's 0.4011, or with a different library, the same results. In Excel, you can calculate it step by step, and there is the same result as well. Or in Python, the same result eventually as well. So it doesn't matter which program you use, any of them will actually have it. I also have on my website a small manual online calculator where you can fill out some values, the chi-square value, the number of categories, and the sample size, and it will then calculate for you what Cramer's fee is. Perhaps in the future I have other software packages as well, but This gives you an indication that no matter which package you use, you should get the same result. How do you then actually interpret that value of 0.4011 or whatever value you had? Now, they will always say that you should look at this depending on the field, but some rules of thumb can be quite useful. One was once proposed by Mr. Cohen in 1988. He actually deals with his Cohen's W, which is not the same as Cramer's V. Cramer's V had this as a formula, Cohen's W has this as a formula. And as you might notice, the only difference is actually here this times K minus 1, which means we can convert a W into a Cramer's V by using this small formula, where K is the number of categories. So you take the W value, any of these actually, and then you have yourself a nice interpretation table depending on, and that's the big difference now, depending on how many categories you actually have. So I've done this calculation for a few values of K. K is the number of categories. And the last row shows basically the upper limit for any number of categories you might have. In my example, Cramer's V was 0.4011 and I had 5 categories ranging from married to never married. So what I can then do is have a look at that table. I have 5 categories, so I'm going to look at this row and I try to find where this 0.4011 fits in, which in this case is in the greater or equal to 0.25. So that means it can be classified as large. So we can add that to our results. This is what I had already so far, and now I can simply add that this can be classified as a large effect size. If you want, you could add the source for this classification system, just in case somebody wants to question you about it. But to some extent, this should be qualified as large. So the chi-square test tells us if everything is significantly distributed, equally distributed or not. And the effect size then tells you roughly how big the difference might be. And that's kind of it for this video. If you have any questions, let me know in the comments. And thank you for watching.